So, to summarize the first topic, we look at from the mathematics of physical model and classify it into subgroups. We focused on the difference between ODE and the PDE from the observational scale. So next, we zoom in further down to the ODE. Well, look, what do we start with? Mathematics model have discrete, continuous, stochastic models, and the continuous model further down to ODE, PDE, and the algebraic equations. And now we go down from here, from ODE, and what kind of model we have under ODE. So to understand the classification for ODE is the starting point for you to understand the ODE, because the organization of the course is always from the type and the method to match how to solve it. We're not going to talk everything about ODE, but we're going to focus the most powerful method in ODE. By using the tool, after you finish this module, you can do pretty challenging research project. So to classify the ODE, keep forwards, not confused. The degree of power of the unknown function. That what distinguishes the first thing, linear or nonlinear ODE. And the 95% of our energy in your course ODE focus on linear, and the 5% nonlinear, those are very special cases we can solve. The bottom line is anything if it's linear, proportional, easy. You can always solve by numerical method, and there's a lot of analytical method you will learn how to solve it. But anything nonlinear, we do not know much. And today, still very active research in mathematics. For example, chaos. If it's nonlinear, you can have all chaotic phenomenon, so-called the butterfly wing problem. And the chaotic phenomenon means there's one location have the butterfly and flip the wing. On the other location, you get a hurricane because that little trigger of this butterfly wing. So that, of course, is a chaotic phenomenon. It's almost impossible to predict. That's why we cannot predict earthquake, hurricane, and tornadoes. That's all nonlinear. The next is called the order of the derivative. If you have the function y(x) you do not know, take a double derivative in the equation is called second order. Take 3 times of the derivative of the unknown function, we call it the third order. That's the second word. The third word is the number of unknown function. If you only have one function unknown, you call it a single ODE. Very easy, just one unknown function, like a calculus 2, pretty much. But most of the time, you get more than one. You know, a moment ago, I showed you the state variables of my AUV and 10 variables. Probably I'm going to have 12. Then you have 12 of the unknown function. That we call the system ODE. By the way, that's what you are going to move towards. Our focus directly to go to the system ODE, but linear. But sometimes we do unlinear. And the third one, homogeneous or inhomogeneous. Homogeneous means you all have the same degree. Non-homogeneous means you're going to mix different degree and all have the same degree of power. In homogeneous, you don't have the same power. That are 4 words. Maybe you need a little more detail. Just go to Wiki, Google it. I'm going to show you a few examples to give you the idea how you're going to name it. So in these 3 examples, they are common, have the u of x as the unknown function. And of course, you need to all have a derivative of this function. Then we call it differential equation. If I give you this equation, that's not a differential equation. That's an algebraic equation because there's no derivatives. So the first one, you have the first derivative. We call it first order. Linear. They're all linear, by the way. They're all first power. Can you see it? There's no square anywhere. Okay? There's no cube. They're all linear. Means first degree of power of u. And this one's a second order because you have the second derivative. This one is also second order. But the difference is here, these 2 are homogeneous. What means homogeneous? Because the power of u all equal 1. See, 1, 1, 1. There's nothing here. 1, 1. That's why homogeneous. Why this is not a homogeneous? Because this has no u, right? Don't have the u. And then this is the u to the first power, 0 power. That's inhomogeneous. Okay. So in these 3 examples, we use all 3 keywords. Linear, that means the first power of the degree. And the order, first order, second order, because they take a derivative twice. Homogeneous and inhomogeneous. So what's next? Now we got the 2 nonlinear systems. Why nonlinear? Why nonlinear? Square, right? That you don't know you have a square. That's nonlinear. But this is the first order nonlinear inhomogeneous equation. So why this is nonlinear? Do you know why? You don't have a square. Why is nonlinear? Get the sign u. You don't know the u. The sign, of course, nonlinear is a wave, right? That's nonlinear. How do you solve this? And that's a pendulum. Well, you cannot solve it, by the way. And in your physical science, that's how you solve it. You're going to approximate the sign u as u by the first degree Taylor series. And then in your ODE, now you can solve it. You double prime x plus g of u equals 0. You cannot solve this. Instead, you solve that. That's how we solve the pendulum problem by approximation. So you got the 2 nonlinear equation, but all the previous 5 are single. You have only single variable. How about the next one? Well, the next one you can write into 2 second order system equation. Now you got the word system. Most of the time we deal with the system. And if you introduce the 3rd variable and the 4th variable, the velocity of x, velocity of w, then you can change it into a 4 variable linear system equation. That's how we're going to do it. And the last one is our goal for this course. I'm not going to talk any of the previous 5, but we directly go to the last type, which is the most powerful, but we get to use the tool. Let me see my time. Okay, I should have about 30 minutes. Now, this procedure, we call it a modeling process. We learned in the first lesson. And I just briefly remind you, this is made by 2 loops. The first loop is the problem solving loop. You go from the problem and translate it into conceptual model by using English, but very specific language, and translate the conceptual model into mathematics model. That will be the differential equations. And then you solve the mathematics equation, or you approximate the solution, and you're going to answer the question. That's the problem-solving loop. And the second loop is the answer justification loop. How do you know you got it right? And you start from your problem, observe something you know absolutely need to be true. And then to backward to see if you solve the math right, the math equation right, and then you trace your conceptual model, see if you made the right assumption, and your translation is all right, and then in the back you try to match what you observed. And we're going to talk more in next hour, but not right now. 2 elements distinguish this process from other process. Number 1, we inserted the conceptual model to increase the traceability of all your procedure between your mental model to the conceptual model, then to mathematics model. From here to here, directly, it's a long way, hard. That's the difference. And the second, in this, we emphasize validation and verification, V and V. That's the other difference. And then in the rubrics of your project, that will be all reflected about the grading system, how well you've done your job.